This presentation is a follow-up to an earlier presentation that I did, which started with the stochastic differential equation for geometric Brownian motion, integrated that to find the equation for the value of the stock price at time t. Then in that presentation talked a little bit about how you would use this to value a European call option via Monte Carlo. So in this presentation, we're going to run through some Excel, R, Python, C++ to actually value a call option. Given what we learned in that earlier presentation, and I'll link to that earlier presentation below. But first, before we jump into that, I want to talk a little bit about what I view as much more important than how to do Monte Carlo is when or why to use Monte Carlo, because this is the thing that's often misunderstood. And I can give you an example of that. Earlier, while I was actually getting my PhD in finance, I consulted for a company because they were valuing an option, and it was the value they were getting was far too large, so they knew it was wrong. So what they did was they tried a couple simulations, a couple Monte Carlo solutions, and they spent some time and money at this. And they got values that were similarly too large, so they knew it was wrong. So they brought me in, and this was one of the, this doesn't always happen, but when I'm talking to them, I could immediately tell them what their problem was. And of course, what the problem was they were making the same assumptions when they were trying to value the option analytically and when they were trying to value the option via Monte Carlo. And if Monte Carlo isn't necessarily magic, if you make the same assumptions, you're going to get the same answer. So that's what we're going to talk about here is when to use Monte Carlo. Then we'll show how to do it, and then I'll show you particularly an example where Monte Carlo is really useful. And again, I view this as much more important as getting a good idea of when to use it than just going through and chugging through some answers, because it's often how it's taught, but sometimes you may do that and it's useless, right? So we want to get a good idea of when to use it first. So starting off, first and foremost here, I'm going to go through, this presentation is online, so you can go through it. I'll move through it fairly quickly. But generally, when you have an analytic, so first thing, when you're approaching a valuation problem is to know if there's an analytic solution. And if there is, meaning an example of an analytic solution would be just an equation, right? So so given the assumptions that go into the Black-Scholes model, we have the Black-Scholes equation for the value of a European call option. So this is going to give us the correct answer given that set of assumptions. So if you're working with a set of assumptions, and given those assumptions, there's an analytic solution, you generally want to go with that. Not always, but well, yes, always. Sometimes what I'm going to say later is the assumptions, you may be in discrete time and the assumption is for continuous time. So, but generally, if there's an analytic solution, use that. When we want to use Monte Carlo is when an analytic solution is unavailable. So we have some problem where there's no analytical solution, or if it's just difficult to obtain. Maybe I could derive an analytic solution, but it may take too much time, so I'll use Monte Carlo. And so the idea here is when Monte Carlo, particularly in finance, becomes very useful is if there's some problem where the assumptions, we can't use the Black-Scholes assumption, we don't want to use geometric Brownian motion, then this is where simulation becomes much more useful. So let's do an example. So when we talk about European option pricing, in the previous video, I went and derived, this is what I derived, right? So let's say we assume this. We assume this is how stock behaves, right? And we assume constant volatility in a complete market and so forth. Then again, we can use Black-Scholes. But so what we're going to do here is we'll value the option via Monte Carlo, and we should get the exact same value of Black-Scholes. So if this is the way stock behaves, right, this is our assuming geometric Brownian motion, we can simulate what this stock value will be at time t by realizing that this Brownian motion term, the b sub t, remember Brownian motion, the change in Brownian motion is normally distributed, so this term here is going to be normally distributed and with a variance of t, the variance increases with time. So it's normally distributed with a mean of 0 and a variance of t. So we can simulate that. We can just simulate a standard normal random variable and multiply it by the square root of t, and that'll give us we'll use this equation, and again, assuming the Black-Scholes world, this is a complete market. What we can do is we can, instead of having the drift term, we can have the risk-free rate for the drift term, and then we'll have an estimate of volatility, again, which you have in the Black-Scholes model, and then this will give us our Brownian motion at time t, and then we can simulate the value of the stock at time t. Now, what's going on here, keep in mind, is this is Black-Scholes is for a European call option, so I don't have to simulate the entire path of the option. I just simulate what the stock is at expiration. So that's what's going on here. So we can go through some of the calculations, and you know what? I'll put up an app here. But so let's jump into some of the calculations here. So what I have here is stock price, strike price, risk-free rate, time, volatility, and then I already have the Black-Scholes solution here. I calculated over on this spreadsheet here, so that's the Black-Scholes calculation. I'm linking to it here. So let's do this. So we know the answer. We know the call value should be $6.32. But let's see if we can find the same value via Monte Carlo, right? So what we need to do, I have this titled outcome. This is you can think of it as the state of the world. So what we need to do is have a standard normal random variable. We need to which in Excel, or I'm using LibreOffice, but it's the same. We can simulate a random draw from a standard normal random variable with an ORMS and then take a uniform random variable, and this would give us the random draw from a standard normal random variable. And so what we can do is say, okay, well, I have the equation up here. We'll input this equation to give us the value, an estimate of the value of, or a realization of the value, the possible value of the stock at time t. So all we need to do here is we'll pull in our values that we used for our Black-Scholes calculation. So the value of the stock today, this is adjusted. I have it in case I want to put a dividend yield in here, times EXP. Now we have, now I need two parentheses, now we have the risk-free rate minus, and I'll just put in vol times vol, 1/2 vol times vol, so 0.5. You could do, the variance, but I'm accustomed to just having vol times vol here, times time, plus what we have is our volatility term here, right? Times, now we have, we need B sub t, right? So this is going to be a realization from B sub t. So this is going to be our normal random variable there, standard normal, times time, right? So we'll go over here and multiply it by time. Good, and that should give us stock price at time t. Now, one thing I want to make sure this is reasonable. So this is the stock price actually declines a fair amount. So make sure my equation is right. It looks right. We'll be able to tell if I miskeyed something. So now we need to get the payoff on the option at time t. So the payoff on the option, remember, is going to be equal to the maximum of, we'll say this is our stock price minus the strike price. And what I should do here is start locking those in 0, right? So that's obviously going to be 0. So let me, before I move on, I do need to lock in some of these values. So hitting F4 here, if you're not familiar with it, I want to lock in every value except for D5. I don't want to lock that in. All right, so now what I need to do is copy this, and I'm just going to calculate this as many times as possible. And now you can see a little bit of the problems with using a spreadsheet, is I really don't want to, I really don't want to see all these random variables, but and then now I have, so that looks like it should be right. Again, the nice thing about this is we're going to know if we did something incorrectly. Having used spreadsheets for quite a long time, I do want to test to make sure my equation is all right. So I'm just going to take the mean of this. And the mean of this, which is average in Excel, 58.62, and that's the idea of this. The way I can tell is I'm assuming this grows at the risk-free rate. So the idea of this, the more I do this, the answer should be near 58 times 1 plus the risk-free rate. So I'm moving a little. Let me 58 times 1 plus in my parentheses there. So it should be about 58.58. Now I'm going to hit F9 and do this a lot, and yeah, so it's a little bit below 58.58, a little bit above 58.58. So it looks reasonable. It looks like my equation is right. I'm going to give it a couple more random variables here. And there might be a quicker way to do this. I would never really do anything like this in Excel unless I'm teaching. Good. So now what we have is, these are kind of states of realizations of things that can happen in the world, and this is the various stock prices, and then this is the call payoff. So what we can do is we sit here and say, okay, well, the value of the call option is going to be the present value of the average of all of these. So first we want to do is take the average of all of this, right? So this is the average payoff at time t, but we want to know the value today. And remember, again, what we're doing here is we've assumed the Black-Scholes world under this. So in the Black-Scholes world, we're in continuous time. So I need to discount this back to today using continuous compounding. So this is, I'll put in there 1 times. So this is, I'm using the present value e to the negative RT, right? So go over here, and I have risk-free rate times time, 6.22, right? So that's my call option today, which is, we know the correct answer is 6.32. Now, keep in mind, this is why generally you want to use an analytic solution. The Monte Carlo is going to give us the right answer, but with some error. And I'm not going to, generally speaking, if you want to reduce that error, you just simulate more random numbers. There's some other approaches, what I'm not going to talk about here, but you see if my answer is right. So I recalculated everything, and now I'm 6.38. I'm a little bit above 6.32, 6.52. So if my answer is right, I generally should be above and below randomly, above and below 6.32, and that looks about right? Now, if I want to be more accurate, all it takes is more random numbers, right? So now keep in mind, I can go all the way to the bottom quickly down to 1 million, but spreadsheets tend to lock up when you start using that many random variables, and if I wanted to use that many random variables, that's when I go over into Python or something similar. So let me just re-grab everything, right? So now, let's see if I'm 6.38, 6.27, right? So yeah, I mean, I'm still getting fairly substantial error. So, but the calculations look correct. So this is how to apply Monte Carlo in Excel. Now the idea again, Monte Carlo, if we make the same assumptions as Black-Scholes, right, we're going to get the same answer. So what you can see here is this is an instance where Monte Carlo is useless, right? You might as well just use Black-Scholes. The only reason I would want to use Monte Carlo is if I want to start relaxing the assumptions, changing the assumptions of Black-Scholes, and I don't have an analytic solution. All right. So now briefly, you might be a finance student listening to this, and so what I usually use this as an example. Finance students should know spreadsheets, absolutely. But I use this as an example of kind of where spreadsheets are not as useful. So the idea here is, keep in mind, we see every outcome here. We don't really want to see every outcome when we do a simulation. So most of the time, this is where I usually show finance students as a good example of when to use something like R or Python. So what I have here is, this is you might not be familiar. This is Emacs org mode. So what I have here is I have the same Monte Carlo calculation I've done in R here, I've done in Python, let me show this. It's folded. This is the C++ version, and I also have in Python, right? So the nice thing about this is, of course, it's much, it's much, we're going to generate a lot of random numbers. The random numbers here is I actually generate a vector of a million. And I don't have to actually see them. So this is it's much nicer to do simulations and so forth in this. It's a cleaner. You can look at what you're doing. So here I'm going to recalculate this. Just hitting CC. I'm going to start an R process in the background, and you're going to see the results. So when I recalculate, you're going to see this change, right? So here, let me recalculate it a couple times, right? So when I do this, it's running this R code and putting the results there. And you can see with a million, we become very close to that 6.32. What was the exact 6.32? Let me see if I can give this a couple more. 6.3198, right? So here, we're getting a much smaller error around this value, 6.3198. And once you start moving over to something like R, it's much easier to say, okay, well let me try 10 million random variables and get closer, right? So now I'm closer, and I could do 100 million random variables, and now it may take a little bit longer. I can hear my processor working here. So but now here I got my solution 6.3206. So it's much faster. Or once we move out of a spreadsheet, it's much easier to use a lot more random variables. I think is that 100 million? Is that already 100 million here in Python? So that should be 1, 2, 3, 4, 5, 6. Yeah. So that's a million. So in Python, this is now I have to start a Python process. That's fine. So here in Python, pretty quick. Python, not to say Python is faster than R, because this is my specific implementation of it, but this Python's working faster here. Let me see if I can go up to 100 million. It's going to still take a second here, but yeah, C.3191. So again, because the number of random variables you have affects your accuracy, you're going to want to do something like this instead of a spreadsheet. Lastly, I have a C++ solution here. Generally, C++ is going to be your fastest. Now, the only problem here is I'm running C++ in org mode, so so this is a C++ implementation of it. When I run this, it's actually going to compile it, and well, that was pretty quick. So this is only a million random variables, so you can see we're very close. And then if I want to up it to 100 million, right? Now it'll take a little bit longer. It should be faster, but I don't know that oh shoot, hit the wrong key. I don't know that my implementation is the most efficient. Is probably not. So let me rerun this. This is with 100 million. So it might take a little bit longer than the Python version, but again, realize it's compiling it, and I'm not writing this for speed at all. But so there we go, 3.1854. So again, we're very close. The exact was 3.19. Right. Yeah, 98. So there's 3 implementations. So if you're a finance student, keep in mind, I would highly encourage you, if you were going to do Monte Carlo, to do an implementation like this. You might think of C++ as being difficult. I'm not using any pointers. I'm not using, we don't have to really worry about data structures and so forth. So I'd argue that this solution is really no harder than Excel, right? You're really not getting into the computer sciencey type stuff. And then particularly, if you look at a solution here, like in Python, right? So, this is our Python solution right here. This is, again, no harder than Excel. You just have to set up Python. And I should probably do some videos, helping you set up Python and installing NumPy and so forth. But I'd highly, in R, because R is made for numerics, you don't need to load any libraries or anything like that. I have to load NumPy to generate random numbers and so forth in Python, but in R, you can just use base R and you get a nice solution here. So, and again, this is no harder than Excel. So I would encourage you to implement this in R, Python, or C++. All right, so that's fine. Back to the presentation. So now we've seen when not to use Monte Carlo. Now the question is just to leave you with a concrete example of when might you use Monte Carlo, right? So again, so this is Black-Scholes. We've already seen. This is an app that I created to show you that the Monte Carlo solution will approach the Black-Scholes solution. So let me reload that and maybe go back to that app. All right, so this is as I increase the amount of random numbers. In this example, the Black-Scholes value is 6.06. These are the call option values. So if I only simulate 50, you can see it's rather erratic. But as I simulate more and more, right, it goes up to a very nice approximation of what the call value will be at expiration, and then my call premium here exactly matches or very close, within a penny, matches my Black-Scholes value, so the difference is 0. So that's fine. That's just what we've seen. Now here's, where might we want to use Monte Carlo? So let's say, so Monte Carlo can be useful when we start looking at path-dependent options. So a path-dependent option would not be a European, right? So a path-dependent option is some option that depends, where the payoff depends on the path that the stock took to get to that final value. So an example of path-dependent options would be American, look-back options, and Asian options. So American, you can exercise at any time prior to expiration. Look-back, it's the payoff at expiration is going to be a function of, let's say, the maximum price that the stock was over the interval. And an Asian option would be the payoff is the average of the price over the interval minus the strike price. So again, this is a function of the average value. So these are just examples of path-dependent options. So let's take the example of a look-back option, right? So again, the payoff is going to be the maximum of the stock price or the asset price over some interval minus the strike price. Right. So now, if we look at a look-back option and if we assume geometric Brownian motion, then we have an analytic solution. And I'll talk about a situation where we still may want to use simulation, but if we have an analytic solution in continuous time, fine. We may not want to. Maybe we should go with that. I'll talk at the end about maybe why we shouldn't. But let's say for now, our boss says no. We want to price a look-back option, but it's not on geometric Brownian motion. It's on this price process. And if this doesn't make sense to you, what I can show you is this is just a mean reverting. So this here is like geometric Brownian motion. So the variance term is like geometric Brownian motion. But what this is saying is the price here. I just have like generic stock price, but this is actually a good model for like electricity. So the price will snap back to some mean value. And again, this is used very often for electricity, because electricity might generally be like $50 per megawatt hour, and it may spike above or below it, but it'll always come back to that $50 per megawatt hour. And that's what you're seeing here. If the mean is $50 per megawatt hour, if the price goes above it, this term is negative, and it'll push it back down. If it's below it, this price is positive, it'll push it back up. This K is the rate of mean reversion, right? So this would be so this would be a good, again, of interest rates, or I've used this for electricity prices. So now there might be an analytic solution to this. Even with this, I don't know, and I might be able to derive one. But I don't know one off the top of my head. So I'd say, okay, well now this is, I could look for an analytic solution if I find one, great. But otherwise, this is now a candidate for using Monte Carlo simulation. So and again, this if I were to come up with an analytic solution for myself, driving it myself, this may take a while. So I sit there and go, okay, well, I'll just use simulation. So what I'll do, and you can read through this. So I set up a little example here. So, what I'm going to do is I'm going to simulate all of these price paths. So, I don't know, maybe I simulated about 1 million price paths here. And then what I can do is I can get a distribution of the max prices, and then a distribution of all the payoffs, right? And then Again, assuming a complete market, I can get the call value, right? So I created this nice, so I can adjust the rate of mean reversion, I can adjust the volatility, I can adjust the average price, and it'll rerun the simulation, it'll give me a call value. But this is the sort of, area where Monte Carlo becomes more important. I don't have an analytic solution off the top of my head. I don't want, my boss doesn't want to pay me to sit around for a month and try to derive an analytic solution, so I can just simulate my way out of it, right? So I wanted to kind of close with this as an example of when Monte Carlo becomes more important. So in some, but let me also talk about, so that's a good example. Now let me also talk about, even if I do have an analytic solution in the look back option, it may still make sense to use a simulation, because the value of the look back option is in continuous time. But what if this option just samples? What if the option says, okay, well, we're only going to look at the end of day price. We'll give you the maximum end of day price. Well, then the continuous time solution is going to overvalue it, simply because what's the probability that the max occurred at the end of the day, right? Well, there's if the max didn't occur during the at one end of day, then the continuous time solution will give us a value that's too high. So even in so if we don't use geometric Brownian motion, then I probably really want to use simulation. But even if it's we're looking at discrete sampling points, then it may make sense to simulate it, because the continuous time will overvalue it. All right, good. So last, in sum, before you really want to use Monte Carlo, you want to get a good understanding of the problem, right? So that you can, once you have a good understanding of what the problem is, then you can start looking into your toolbox and saying, what's the appropriate solution, analytic or simulation? And I do this presentation, I talk to students about this a lot, because in other courses, other business courses, I see them doing simulation software. And, if you assume a bunch of random variables are normal, well, then, if I take a sort of a linear combination of these normal random variables, this is going to be a normal random variable. So I could just calculate it without doing any sort of simulation. So again, I've seen it in industry, and I've also seen it quite a bit in academia, where people are doing simulations when an analytic solution is readily available. So it's a good, now if you want to sit there and say, okay, well, now I'm doing some business simulation, but I don't have normal random variables, and I'm going to, ultimately my solution is going to be a linear combination of a bunch of different types of distributions, then maybe you want to simulate it. And so this is where, in closing, it's a good understanding of the problem. Get a good understanding of the problem, and then you can decide whether simulation is going to be useful in this scenario. Good. All right. Any questions, feel free to ask them. Great. Have a great evening.